Here in section 11.7, we're going to be developing a general strategy for testing whether a series is convergent or divergent. So at this point in this chapter, we've developed a handful of different tests for testing a series. So we have quite a few options in our toolbox. And so our goal now is to figure out how we can utilize those in the most efficient way to test whether a series is convergent or divergent. So given any series, what's the best way to approach it and determine whether it's convergent or divergent? And so to start, we'll look at the simplest case, which is the case when we have a p-series. A p-series is a series of the form 1 over n to the p. And we know exactly when it's convergent. It'll be convergent when p is greater than 1. And it'll be divergent when p is less than or equal to 1. So if we can recognize that it's a p-series, well, we know right away whether it's convergent or divergent. And another case that's very simple or very easy to determine whether it's convergent or divergent is the case when we have a geometric series. And a geometric series maybe is not always going to be written in this form, ar to the n minus 1 or ar to the n, but usually we can recognize a geometric series when it's in a form that involves some constant raised to the power of n. And then our goal is mostly just figuring out what the common ratio r is. If the common ratio r is less than 1 in absolute value, then we know it's convergent. Otherwise, if the common ratio is greater than or equal to 1 in absolute value, then we know it's divergent. And you may need to do a little bit of manipulating to get the series in a form where you can recognize what the r value is. Now, a slightly more complicated variation of those first two cases might require us to use a comparison test. So in other words, if it's not quite a p-series, but it resembles a p-series in some way, then oftentimes we can do a comparison test with a p-series. Or similarly, if it resembles a geometric series, but is not quite a geometric series, then we can use one of the comparison tests to compare it with a geometric series. So one thing to look out for is when we have rational functions. Rational functions can always be compared with a p-series, right? So for instance, if I have something of the form, say, let me just kind of randomly make up some random terms of a rational expression here. Okay, well here's one just kind of randomly made up, but if I wanted to test this, well, what series would I compare this with? Notice it's just it's actually got a radical, and therefore we can compare it with a p-series. And the way we would do that is we can just focus on the dominant terms in the numerator and denominator. So in this case, we would compare it with just taking the dominant term here, 5n squared, and then taking the dominant term here, which would be square root of n to the 5th, which notice that this simplifies to a p-series, because the square root of n to the 5th is the same thing as n to the 5 over 2 power. So this would reduce to just a p-series of the form 1 over n to the 1/2 power. Right here, notice that the 5 over 6 doesn't really make a difference. It's a constant that you can essentially pull aside and just focus on 1 over n to the 1/2. So it's a p-series, and we know it's a divergent p-series. Another thing to keep in mind is that with the comparison test, it requires that the series has all positive terms. So if I have a series that does not have all positive terms, but I want to use a comparison test, I can consider the absolute value of the terms instead, in which case then I'm really testing for absolute convergence, which is a stronger form of convergence. So if we can show that the series is absolutely convergent, that implies that it is also convergent. And some other things to consider is if we can see at a glance that the terms of the series don't go to 0, then we should just say it's divergent, because we know that if the terms don't go to 0, then automatically we know it's divergent by the divergence test. And another thing to consider is if we notice that it's an alternating series, right? If it contains a factor of the form -1 to the n minus 1 or -1 to the n, then we know it's an alternating series, and so the alternating series test would be a really easy test to apply. Usually we can get a result from the alternating series test very easily just by observing that Bn is decreasing and goes to 0. For a series that involves factorials or some constant raised to the nth power, then a good choice would be to use the ratio test. Remember, the ratio test is not always conclusive. Sometimes it might give you an inconclusive result, but the cases when we know it will be conclusive are the cases wherein we see a factorial like n factorial, or it includes a constant raised to the nth power, like maybe it has something of the form 2 to the n, something like that. Then we know that the ratio test will simplify into something that doesn't go to 1. So, but if we see that as n goes to infinity, the ratio an plus 1 over an goes to 1, then we have to consider some other test, so the ratio test will not work. Notice that'll actually be the case for all rational expressions or algebraic functions of n, so things including radicals, which again, we don't want to use the ratio test for those because we actually know a comparison test will work better for those cases. And similarly, we can also consider the root test. So if our series has an expression of the form bn to the nth power, so it has an nth power on it, then we know the nth root of that will simplify into something nice that we can perhaps easily take a limit of, and so the root test will be useful in those cases. And then lastly here, if we notice that the series is easily integrated, then in other words I can evaluate the integral from 1 to infinity of f of n, where f of n is the terms of the series, then an integral test would be an easy test to do. So the main thing here is that it's something that we can actually integrate. Keep in mind that evaluating integrals is not always an easy thing, and so this test would not be something that you can always apply.